Okay, for this talk we have Jose Ezquiaga. Do you want to quickly introduce yourself, Jose?
Yeah, of course. So I'm a postdoc at the University of Chicago. I finished my PhD last summer, which I did on the Universidad Autónoma of Madrid. And yeah, my background is in theoretical physics and cosmology, and I study gravitational waves in particular and early universe physics. And today I will be talking about this last topic.
Yeah, so do you want to, for just a couple of minutes, sort of summarize what you'll be talking about in the talk?
Yeah, so essentially, I will be talking about a recent paper I did in collaboration with Juan García Bellido and Vincent Benan from Paris. And there what we did is we developed a method to compute in a generic way the tail of the inflationary curvature perturbations. And this is important because, for example, in the context of primordial black holes, when you want to assess how many of them are formed, then you need to look for fluctuations which are larger than a given threshold. And then in that case, the tails of your distribution are really the only thing that matters. So we developed a new technique to compute this exactly, and we apply our results to several models.
Cool. So do you want to bring up the slides and start telling us the details?
Of course. So as I was saying, primordial black holes, one of the ways you can form them is by having large fluctuations, right? And when we think of large fluctuations, of course, we have to remember that we have some constraints, right? We know from the CMB that the amplitude of the primordial fluctuation has to be 10 to the minus 9. But this is only on a really small range of scales. Mm-hmm. So if we think of, for example, the number of EFOLs, this just corresponds to 5 to 7 EFOLs range. We will have better constraints in the future with larger scale structure, with epoch of ionization. But when we talk about small scales, we really have no constraints. Mm-hmm. So it's really in this region of small scales where features in the primordial power spectrum could happen, leading to the formation of primordial black holes. And these primordial black holes, they have gained a lot of attention recently as a candidate for the dark matter, a fraction of them. But to myself, I think what is most interesting is that if they were to exist, they would give us like a unique fingerprint of a period of inflation that we could not access otherwise. Mm. So it's opening, it would open a window to inflation in that sense. So we, in order to determine the fraction of primordial black holes, we ask the question how many of the primordial fluctuations are above a given threshold, and this threshold depends on the environmental conditions when these fluctuations re-enter. But let's avoid the details there. Essentially, what we want to know is how is the tail of our distribution, right? And something which is important here to account is that we are in a regime in which, because intrinsically we are asking about large fluctuations in which non-perturbative effects are important. So the standard techniques that are used to compute the power spectrum, for example, around the peak of the distribution, are no longer valid here because we are in the regime in which fluctuations are large.
Moreover, I guess one important point, I guess, to keep in mind is that even though the sort of variance of the fluctuations is large, you're still talking about the primordial black holes forming at very, very rare, like 5-10 sigma tail of something that is itself quite large. So it really is far into the tail, even of a large variance distribution, right?
Absolutely, absolutely. So and the important point, yeah, that's a good point. And also that once you are that far in the tail, then any modification of your statistics is crucial. Like if you have a non-Gaussian corrections, as we will see that will arise, then your predictions change dramatically.
Yeah, even though they might be utterly irrelevant if you just want to know the variance.
Yeah, so even though you would think, looking at the peak of your distribution, that you have something which is really similar to a Gaussian, when you go to the tails, as we will see, quantum diffusion introduces an enhancement of the tail which make it decay exponentially. And this exponential decay is very relevant for these questions, right? So since we are living with very rare but large fluctuations, the formalism we apply is that of stochastic inflation. Because in stochastic inflation, you have an effective theory that can allow you to describe the long wavelength perturbations as affected by the short wavelength perturbations that introduces a noise. So you are encoding all the quantum dynamical effects in this noise term, and this is going to change your classical picture, right? So in the standard single field model of inflation, this is what was worked out by Starobinsky in the 80s, right? So instead of working with the inflaton field, it's more convenient for our case to do this stochastic formalism, but for the number of e-folds. So you convert your curvature perturbations into time, into number of e-folds, and then you see how these fluctuations are stochastically distributed. So you need to solve a Fokker-Planck equation, and what we will be looking for is for this distribution of the number of e-folds given an initial field value. So one of the key points that we make in this paper is that this probability density function of the number of e-folds or the curvature perturbations, you can write it, you can represent it in terms of a series of exponentials. So you are kind of expanding around the tail, and that the exponents of these exponential are determined by the poles of the characteristic function. And the characteristic function is just nothing but the Fourier transform of your PDF. So this, which is kind of I mean, it's a mathematical property, but it turns out to be very useful, because if you want to compute your tail in an exact way, you are expanding about the tail. I mean, this description is not going to work very well for the maximum, but for the tail, it's going to work nicely. Then the only thing you need to do is you need to look for the poles of your characteristic function. And this is very simple. For example, you just take the inverse of your characteristic function and look for the zeros of this function. So this is kind of the framework we use. And then this allows us to obtain, for example, predictions for different potentials. We focus in this paper on slow roll potentials, although in our formalism in principle can be extended. But we focus on a slow roll potential, and then the simplest thing you can do is just a flat potential, right? So this, in this case, you have all the results which are fully analytical. And what you can see, if you represent your potential as a flat region between the end of inflation and a given upper value, then the tail of your distribution is going to be precisely determined by this duration of your flat potential. So the nice thing of this is that you can get everything very precisely and exact analytical results.
I think I might ask this question during the conference itself, but like the background effect here, then, I mean, if I was just to do the normal naive slow roll thing here, I get a V prime in the denominator and my variance goes to infinity, right? When I've got a completely flat potential.
Exactly. Yeah. That's an excellent point. So in the classical picture, this this potential is like is not well behaved, right? Because you have this divergence. But when you are solving the stochastic within a stochastic inflation, you can see that indeed you can solve the problem, because what happens is that the dynamics is dominated by the quantum diffusion through the noise instead of the drift term, which is the classical term. So the drift term is what gives you this divergence, but since you are dominated by the other term, then you can have a solution which is perfectly fine. So that's a good point.
I definitely have more questions on it, but I will wait for the conference.
Okay, of course. So this kind of toy model, what allow us is to get some analytical understanding of how the tail behaves, right? And for example, we can apply this for a more realistic potential in which you have an inflection point. So for this, what we do is we look for the region of this potential around the inflection point, which behaves similarly to a flat potential. So we look for the region which is dominated by quantum diffusion. And then what we can take is the analytical results from the flat case, and we can apply them. And you can see in this plot, this corresponds, so the just the flat approximation are the dot lines, which can be compared with the full PDF. And they, in this very simple and kind of, simplistic approximation, you can see that already you get a really good approach to the real value. Of course, you can get something really nice just by computing the pole, the leading, the lowest pole of your characteristic function, and these are the dashed lines. Mm-hmm. So the dashed lines, just by computing the pole, you can get precisely the tail. And with these analytical formulas, you can get more or less the order of magnitude. And so this is kind of the way we approach this problem. So combining these different techniques, and we do the same for a constant slope potential. The new thing here is that because you have the slope, then your eigenvalues, the poles of the characteristic function, they get shifted, and this what means is that your tail, it gets suppressed. And we use this linear potential also to as an approximation for a inflection point potential, which has also some slope. Mm-hmm. And in the paper, you can see a lot of details about this, and I'm also happy to give more details during the conference. Cool. But just moving forward, so what we have seen is that the PDF can be expanded in the tails as a series of exponential, and we can get very easily these exponents, right? Of course, the other, I forgot to mention, I was focusing all the time on this lambda n, which tells you the slope of your tail, but also we can compute these coefficients an, which tells you the amplitude. Mm-hmm. So something which is also very nice is that the slope of the tail is a universal property of your potential. So you will have an exponential tail with a given slope for all the scales of your potential. But then, of course, this tail will be only important in the regions in which you are dominated by quantum diffusion, and this appears through the scale dependence of your coefficients A of n. So only in the regions where quantum diffusion dominates at the smallest scales, for this case, for the case of primordial black holes, is where this tail is large enough to have some effects. So from the PDF, you can compute the abundance of primordial black holes. So just computing the fraction which is above the threshold, and is this simple expression which is square in this red box. So notice here that because, again, we have this exponential decay, then this is very different from the standard Gaussian approximation, in which your abundance decays with the exponential of the square, the negative square of the fluctuations, and here is just with the exponential of the negative perturbation. So something with all this machinery, so one of the questions that we ask is, okay, but for these inflection point potentials, what kind of predictions we get, right? So in particular, we analyze the parameter space of this simple parametrization that we have done in terms of a cubic potential. And then what we find is something interesting, is that in the region in which a slow roll is satisfied, which is not all the region of the parameter space, because when you have an inflection point, you can enter the inflection point with a lot of inertia, and this brings you out of a slow roll. And also, as you get to the inflection point, you are very, you decelerate a lot, blah, blah, blah. Okay, but in the region in which you are within a slow roll, what we find is that you always overproduce primordial black holes. So this would correspond, so here in this plot, the region which is shaded in gray is the region where a slow roll is violated. And in the region that is below this slow roll violation line, then you can see that there, the abundance, the fraction of primordial black holes, this beta, is always very large, it's order 1. And we have constraints on this abundance, which has to be like 10 to the minus 9. Well, it depends on the scale, but always it has to be a small number. So here we can see that for this model, if you, for the sector of the parameter space where slow roll is preserved, then you always overproduce. So this you can rule out these models in that sense. And we do the same for the cases in which you have, instead of a flat inflection point, you have some tilt. And then we find essentially the same conclusion. So of course, something which is interesting, and we want to, we are working on it, and we hope to get results soon, is to precisely analyze the other part of the parameter space in which a slow roll is violated. And with our formalism, I think we can do it. You just need to extend a little bit some of the parts, but conceptually, we will be able to also solve this question. So this is all I wanted to say, essentially. So if we want to summarize the talk, maybe with like a headline, we could say like the exponential tail induced by quantum diffusion impacts the primordial black hole fraction. So we develop a method which is generic and non-perturbative, which allow us to compute exactly the tail of the PDF. And this tail we found that is intrinsically non-Gaussian and also is inevitable. We apply this analysis to single field models of inflation that satisfy slow roll. And we found some analytical expressions that we test again numerical calculations. And we found that, as I was summarizing in the previous slide, that for inflection point models that satisfy a slow roll, they will always overproduce primordial black holes unless the slow roll is violated.
On that last point, was that also true for the tilted inflection point, or just the flat inflection point?
No, for both of them, we found the same conclusion.
Okay, interesting. So this seems potentially to have huge consequences, right? Like if, there's a lot of inflection point inflation models out there that are claiming to fit the CMB. I mean, when I say claiming to fit the CMB, probably do fit the CMB, but then you're saying that far into the tail, they'd be producing primordial black holes.
Right. I mean, so we are currently working also on the impacts for that would have him at CMB scales. I don't know exactly which models you are talking now.
I mean, this is again something that it's better to have in the conference, but like all of these sort of MSSM inflation models from 10 years ago that had inflection points found within the MSSM minimal supersymmetric standard model.
Okay, right.
Which may have all been ruled out by the LHC by now, for all I know. But
okay. Yeah, but I mean,
let's hold this discussion until the conference. I'll bring some references and we can look into them, and you can say whether you think that they're. I mean, it'd be very interesting if they're not viable. There may be obvious reasons why your work doesn't apply to them that I'm just not managing to pick up in 20 minutes. So.
Okay. Yeah. But something which is, I want to emphasize is that this tail is going to be at all scales. The key point is that depending on which scale you are, the amplitude is going to be larger or smaller. So that is, I mean, what you have to check.
Cool. I'll just, yeah, thanks for the talk, and I hope everyone will find it very interesting.
Thank you for hosting it. Essentially, you want to do something like the integral that is represented in this slide. So pictorially, what you want to do is what is happening on this plot. So you want to know.
I'm sorry. At the moment, I still see your title slide.
Oh, really?
Yeah.
Oh, wow. What is that? Can you see now that I'm changing?
No, still the title slide.
Oh, wow.
I'll edit this out afterwards. Don't worry about it. Yeah, I don't know. Yeah. I see your title slide.
Oh my goodness. Stop serving. Let me. Why? Okay. Yes, sorry about this.
No worries. Like, this is an excellent proof of why we made the right decision to do the recordings in advance. So that, like, imagine if this was happening in the actual conference and it's like, oh, I can still see your title slide.